Hello and how are you? Welcome to this tutorial in which we are still handling topic number 37, which is cathode rays and cathode ray tube. Basically, this shall be our final section in which we are covering the topic, after which you should now be able to sum up everything in the specific objectives that you have been covering to be able to keep you acquainted with the knowledge that is required of you. I'm your tutor, Joseph Adeli. As we begin, let's have a quick word of prayer. Father, Lord in heaven, we invite you in this session. We ask you that you may be able to guide us in learning, because you are the greatest physicist we have ever known. May you be able to teach us with the stillness of your voice. Yes, I may pray. Amen. Basically, the specific objectives by the end of this topic, which by the end of this tutorial you should be able to, 1, describe the production of cathode rays. I believe that you know. You should also be able to state properties of cathode rays, explain the functioning of a cathode ray oscilloscope, which we are now going to tackle in this tutorial, and also the television tube. You should also be able to explain the uses of cathode rays oscilloscope. I believe the explanation of the functioning of a cathode ray oscilloscope was explained previously, just with the deflection and all the specific parts. Now we're going to look at the television tube in this tutorial, and also we're going to solve problems involving cathode ray oscilloscope. So I believe by the end of this tutorial you should be able to sum up everything. Now, what are the uses of the CRO, or basically the cathode ray oscilloscope? The first use, the cathode ray oscilloscope can be used as a voltmeter. Now, how is this basically done? Now, you find that we explained something about the time base, whereby the time base simply means the deflection system in which acts on the X plates. So basically, the X plates were the one that run horizontal. They deal with the horizontal deflection. So a time base is switched off. So it means there is no effect of the cathode ray crossing the horizontal deflection of basically the X plates. So basically it will just be moving up and down, basically because the time base is switched off, the X plates are earthed, and the voltage to be measured is connected across the Y plates. So the only that has effect is the Y plate. So you shall only observe vertical deflection on the screen of the CRO. So that's to give you a glimpse of what is basically happening. So the vertical displacement of the spot on the screen is measured by the voltage determined using a specific formula. Now let's basically get practically what we have just explained here. So we have said that the X, if I just simply draw a graph here of how this, you basically know the graph. This is basically the X variable, and you have the Y variable like this. So if I assume that this is just what you have as a sketch, but on the screen you just observe several boxes, you will not see a Cartesian plane. If I now have this so that you may be able to clearly get what I mean, the X, you shall not see something on the wave moving on the direction of the X. You shall only see something, or shall only see a graph or points moving along the Y plane. You shall only see like this. They shall just be moving up and down, up and down, up and down, up and down, anywhere. They can even be in these spaces. That's if you'll be able to know what they specifically mean, the values there. You shall not see them moving across the X. I believe that is just quite clear. You shall not see them moving like this. That is just wrong, because the X plates have been earthed, the time base has been switched off. They are not basically functioning. So basically the formula that we are using will be voltage is equals to displacement multiplied by sensitivity. Sensitivity is basically, we spoke about the Y gain knob. So the level of sensitivity is selected using the Y gain knob. So basically when you tune the Y gain so that you may be able to have the machine to be able to detect very small values, you set it to a very high tension. We spoke about the vertical deflection and how it works. So you ensure that the field in between those particular plates and the frequency in which they change is very high, and that is tuned by the Y gain knob, which automatically connects the input signal through an amplification system, so that it can be able to be visibly seen on the screen, such that if there is any slight voltage recorded, it shows it immediately with that small deflection, so that the accuracy is very high. So that's what we mean by the amplification system. So this ensures that even very weak signals are amplified to the levels where they cause measurable deflection of the beam, such that you can be able to notice it very clearly. Now let us look at some various advantages that the CRO has above the conventional meters that we basically have. For example, in the lab, you might be conversant with the various meters, the voltmeters that are in the lab. Notice that those voltmeters have some various defects. One, it has resistance, high resistance, so you have to connect it in parallel so that you minimize the resistance. Another thing, you'll also notice that the amount of the sensitivity of that voltmeter, let me start with that, is very weak, because it depends on the swinging of that that pointer. And also, if you have very high voltages, it shall get damaged. So such things are some of the things that you don't want. So you need to respond to the sensitivity of the voltage to depend with the inertia that is caused by the voltage there. And then you find that it will only measure direct current, because in the lab you only have direct current because of the dry cells. But if you have alternating current, when it starts swinging up and down, it tends to be able to it tends to not work very well. Now, the first advantage, so that you cap all those particular challenges, find number one, it has infinite resistance and does not therefore take any current in. So this infinite resistance and does not take any current. So this means it does not therefore interfere with the current, with the circuit in which it's connected. So there's no worry about the circuit connection like the voltmeters. Number two, it can measure both direct and alternating voltages. So whatever it is, if it's alternating or direct, it will just measure it. It will not have the challenge of saying that it will keep on swinging forth and back, and then immediately the spring that is holding that particular pointer gets damaged. So there's no that worry. Number three, it responds instantaneously, unlike ordinary meters whose pointers swing momentarily about the correct reading due to inertia. So the moment it records an alternating current, you notice that alternating current has various frequencies, goes positive and negative. So there's no challenge of saying that the accuracy will be very slow. It will record all of them instantaneously. It will not have a challenge like the normal voltmeters or the conventional meters that we are used to. And then it can measure large voltages without getting damaged. Notice that the normal voltmeters that we know of, the moment you apply a high voltage that not it can measure, it just blows off. So that is the four advantages that we have of the CRO above the normal conventional meters when it's used as a voltmeter. So notice how is it used as a voltmeter. You have to switch off the time base, the X plates you earth them, and then the voltage to be measured is connected across the Y plate, so that you may be able to denote it clearly. Let us get the next use. It's used in determining the frequency of an AC signal. Now, how is this done? The signal is fed into the Y plates of a CRO with the time base on. Now notice this case, we have the time base on, meaning if you have the graph, the Cartesian plane sketched, both of them will be shown, meaning you'll have a curve. In the previous one, we had a vertical line, which basically is several dots that show the different voltages that are measured, but it ends up making a line, for example, depending on the frequency. But in this case, we now have both the Y plates and the X plates on, because the time base is on. So the time base control is then adjusted to give one or more cycles of the input signal on the screen. So basically we can have such an example whereby we have our curve in this manner. So there's both the Y axis, if I may say so, and then the X axis. You basically know how to get that from waves. You get the total amplitude, the top, the total amplitude from the peak to peak, and then divide them by 2. Notice that this will be 3 plus 3, this is 6, divided by 2, the mean position comes here. I believe you have just seen the gymnastics that I've simply done, because you're going to apply it in one question forthcoming. So you notice that we have both the X and the Y values all represented on our screen with the CRO. So that's basically when you are calculating for frequency. So the time t, notice that frequency has a time aspect, only that it's reciprocal to period. So you start by getting the period. For example, if you are getting frequency, which is the unknown term. So the time t, capital T, which is the period of the signal, is then determined by relating the trace of the signal on the screen with time base setting. The frequency f can be calculated with the formula f is equals to the reciprocal of 1 over t. Now let's basically explain what I've simply said. So the time t will be associated with the time base, whereby the time base is associated with the X plates, and the X plates, because you're using the terms of the graph, shall be the X values. So the X values here, if I'll have the time base being a particular value, they shall be given in, for example, let me say seconds per division. So each of these divisions shall represent that specific value of the division, and you shall be able to calculate them the same way you usually calculate the period of a wave, and I believe that will be much clearer when you get to examples. So basically the formula that you use is frequency is the reciprocal of period, and the period you can be able to get it direct from the graph by calculating for the time of one complete wave. After getting the one complete wave, now get the frequency, the inverse. You shall be able to calculate it more clearly. Now we have a question here. We may pause the video if you don't mind, so that you may be able to try working on it before I give you the solution. Now notice that you have been told, given the figure below, the time base control is set at 100 milliseconds per division. Determine the frequency of the AC signal on the screen. So basically, let us first have on our fingertips everything that we need. First, we begin with something known as the numerical data. I believe I sent you a document about how to solve physics problems, and not only physics problems, but any other solution, any other things, or any other terms that can be able to apply the document that I sent you earlier. If not, please ensure that you get that particular document. So we begin with the numerical data. The first thing you'll notice that we have been given in the question a time base setting, a specific time base setting, which is basically 10 milliseconds per division. In the question I've given you 100 milliseconds, which is I believe the answer will just be half of what you have, but it's wrong. Just try working out with 10 milliseconds. It should not be 100, it's 10 milliseconds. So try working out with it if you used 100 milliseconds, and see which answers you'll be able to get. You may, again, if you don't mind, may pause it the second time so that you just get the right values. So basically, you'll find that the time base setting is 10 milliseconds per division, which if you get everything with standard form, you shall have 10 multiplied by 10 power 3, whereby 10, you know that milli is 10 power 3, so it will be 10 by 10 power negative 3 seconds per division, which is simply 10 power negative 4 seconds per division. So it means each of these division shall be 10 power negative 4 seconds per each of these division. So that is the first thing. So the second thing that we need to note is that when you're getting frequency, we require the period. And how do you get the period? Period is simply the time taken in getting one complete oscillation. So one complete oscillation is basically from here all the way up, down like that, and up to here. So it means we'll first start by calculating the total time taken in getting that full wave. So from here we'll have 1, 2, 3, we have here 4, this is 5, this is 6, this is 7, and finally we have 8 divisions. So basically you have one complete oscillation in this diagram, and that one cycle is equivalent to 8 divisions. So the question is, first we get the period, and the period will be equal to the number of divisions multiplied by the time taken. Basically you'll notice that in this case you'll have 8 by 10 power negative 4, whereby each of, you know that how you, I believe you know how to get how all of them, because each of these division is 10 power negative 4 multiplied by 8 gives you the total time. So if I just do something known as dimension analysis, I believe in the document still there's something I have explained about dimension analysis. Notice that division and division cancel out. This is just to ensure that you have the right formula that you created, because this is a formula that you'll not get in books. You have to know how to derive them. So division and division cancel out to remain with seconds. It will remain now as 8 by 10 power negative 4 seconds. That gives us the period. But what is the frequency? The inverse of that answer will have that, and basically the frequency will be 12.8 Hertz. So always arrange your questions in a specific form so that you may be able to get it clearly, and you can refer backwards if there was a challenge with your calculations. Next, you may pause the video if you don't mind to do the second assignment too. So take note, a DC voltage of 50 volts when applied to a Y plate of a CRO causes a deflection of the spot on the screen as shown in the figure below. So they have shown you where the mean position is that is 0 volts. So determine the sensitivity of the Y gain. Number 2, show what will be observed on the screen if an AC of peak voltage 40 volts is fed onto the Y plates. So basically here they're asking you draw the graph, just trace and show what will be seen on that specific screen. So let's begin by the numerical data still. Question 1, determine the sensitivity of the Y gain. So in the first case, you need to get an assumption that will be able to give you a workout in this question, because you notice that it's somewhere in between. The spot is coming in between some boxes here, but we can begin by counting this. This is 1 and that is 2. Now from our Form 1 physics, topic number 2, measurement, you are able to know that how to be able to estimate values in which the accuracy cannot be able to get. So our accuracy here is only 1 division, but how do you then get these other small values? You cannot say a third of the division unless you have subdivided it much smaller that you may get it. So anything in between here is basically a half. It's assumed to be a half. So basically you'll have here a half of a division, or basically 0.5. So that's what we start with, an assumption that the spot deflection on the screen is 2.5 divisions, and from the question the voltage is 50 volts. So determine the sensitivity of the Y gain. Now how do we get about this? So the sensitivity shall be given to us by voltage divided by the number of divisions. Believe this one from the previous formula that you have been given. You can be able to play around with it, because voltage is equal to displacement multiplied by sensitivity. So sensitivity will be voltage divided by displacement to give you the sensitivity there. So the sensitivity will be 50 divided by 2.5 divisions, giving us 20 volts per division. But what was the question asking us to get? The sensitivity of the Y gain. That's going back to the question. So basically you have the answer of the question. So the sensitivity of the Y gain is 20 volts per division. Question number 2. Show what will be observed on the screen if an AC of peak voltage 40 volts is fed onto the Y plates. So the numerical data would have been given. So we have a 40 volts peak voltage. We also have a Y gain of 20 volts per division from the previous question. So number of divisions will be equal to 40 volts 40 volts divided by 20 volts per division. So notice that the voltage and voltage will cancel out, because you'll have to get the reciprocal of the 20 volts per division, whereby volt and volt will cancel out. I believe you know how that one will happen, because if I have V divided by, into brackets, V divided by division, this one shall result into V multiplied by division divided by voltage. So this V and that V will cancel out, you remain with division. So that's why we have two divisions. Now this one will enable us to plot on the graph. So if we have this, what shall be able to be observed? So this one shall start here and it shall move 2 divisions up. But now we need to be able to get something. After moving 2 divisions, notice that the voltage is AC, hence we shall have a plus or minus 2 division from the 0 level. Now we have to note, where is the 0 level? The 0 level is here, so it shall move 2 divisions up to here, and it shall go back and move to the opposite direction 2 divisions down. So you shall be able to observe a horizontal line of 4 divisions, only that the amplitude is simply 2 divisions. I believe you can notice that. So that is why our answer now comes to lie to this. This shall be our answer, because our 0 mark is this. This is the 0 mark. Assignment number 3. You may pause the video if you don't mind, to be able to work out this. Now you have been told that the figure below shows a trace on the screen of an AC signal connected to the Y plates of a CRO with the time base on. So here we should work out something to do with frequency of the signal. So given that the time base control is 5 milliseconds per divisions and the Y gain is 100 volts per division, determine the 1. Frequency of the AC signal, number 2. Peak voltage of the input signal. Now note, in this case you don't have the mean position, so believe you knew how to plot the mean position, get the total amplitude, peak to peak amplitude, and then divide by 2. So peak to peak here shall be 1 2 3 4 5 6. So 6 divided by 2, that is 3. So the mean line is here. So that is your 0 mark. That is the first step. Now the next step is getting the numerical data of each step. So what do you have? Let us first begin with that. So in the question we have been given the time base control, which is 5 milliseconds, and 5 milliseconds into standard form is 5 by 10 power negative 3 seconds per division. Number 2, how many divisions have been covered? Because we are looking for frequency, and frequency, first step from the graph will be period. So we have to get the total time taken, and the total time is given by the x values, which shall come out of the number of divisions. So let us begin counting. This is where the graph begins. How many oscillations do we have? Because we only require 1 complete oscillations. So let us get how many oscillations are here. We found out that the mean position is on this. So up to this point, if you begin here, up to here you have a quarter of our wave. Here we have a half. You have 3/4. You have a complete wave. 1 1/4. 1 1/2. 1 3/4. Total of 2 complete waves, 2 complete oscillations. So we have 2 cycles. Now, how many divisions do we have across this particular wave? Now, we have 2 methods of applying this. You can either work now with one complete wave and you have the number of divisions multiplied by the time-based control, or basically you can work with 2 oscillations, then remember to divide by 2. There are two methods. So I'll use one of them, but I'll be able to explain at the bits of where you'll be able to apply them and how to be able to get the same answer using the 2 different methods. So number of divisions are 8 divisions. If you count them, this is 1, this is 2, this is 3, this is 4, this is the 5th division, 6, 7, and the 8th division. So the one complete oscillation is simply at this point. You can use four divisions and remember to apply with 1 oscillation, or if you can use 8 divisions, you know that there are two oscillations. That means you divide by 2 at the end, so that you may get the period from the definition. I believe you know the definition of period. So basically that is what we can denote from the question. So what is the frequency? Start by getting the total time, which shall basically be 8 divisions multiplied by 5 by 10 power negative 3 seconds by division. Division cancels out, you'll have 4 by 10 power negative 2 seconds. That is the time for 2 oscillations. So we'll start by dividing it by 2 so that we get the period of the wave. Or basically, notice if I come and say 4 divisions here, it will simply give me 2 seconds directly. It will not have a challenge of dividing by 2. You'll just get the period directly. So this is just a long cut for no good reason, but that's just to be able to give you an upper hand. So reciprocal of that shall get the frequency, which is 50 Hertz. So basically that's our answer. Let's get the next question. What is the peak voltage of the input signal? So number 1, what do we have? In the question, we have been given the Y gain, which is basically 100 volts per division. And then something you can note from the graph is from the displacement. What is the amplitude of that graph? If you note from what we calculated, this is 3 units. So basically, the deflection is 3 divisions from the 0 level. Here we want to get the Y gain. So what will be the particular formula we'll use? So basically the peak voltage will be equal to the Y gain multiplied by the number of divisions, which is basically 100 volts divided by divisions multiplied by 3 divisions, giving us 300 volts. That gives us the peak voltage. So that's basically what we need to know. Now let us get the television tube. The television tube, there is something very, very important you need to note from this, that the television tube is a cathode ray tube with the following modifications. 1, the deflection of the spot by magnetic coils, and number 2, the incoming signal from the aerial is fed into the grid. Now, if you remember, we just tackled something. I gave you a hint about the television and how it was in the analog system. Find that it had a very big back because of the nature of the cathode ray. But we shall see the modifications that have come about to be able to improve the TV into what you know as a flat screen television. Now, the deflection of the spot by magnetic coils. So these are positioned in pairs to effect vertical and horizontal deflections of the beam. Now you note that this is what we have covered as the cathode ray oscilloscope, and this is what was originally the television that we used to have. But to reduce that particular distance between the hind of the TV and the screen, this particular input signals and the anode were combined to be able to make that distance smaller. But it was not only about the distance being small, but it was making it more effective, because if you use magnetic coils, it makes it more effective. Let us get how effective they are. But first of all, the diagram in which they are used is this. So the electron gun is here. From the electron gun, we'll basically just have a magnetic coil. So the magnetic coil serve as one, the anode, not the anode, because the anode is in the electron gun. So we basically now have the input, the X and Y plates. So these particular deflecting coils give us those particular deflections. So why are we using the magnetic coils? Magnetic fields are preferred to electric fields as they give a wider deflection of the beam. You can just adjust them and have a wider beam. But if you have the plates, they are rigid. I believe you can see what I mean by rigid. So this makes it possible to work with a wide screen with a relatively short tube. So with the time, if you just check your television, you can see that those are some of the modifications that have been done. Let us get the next part. The incoming signal from the aerial is fed into the grid. So I believe from the structure that you have noted, we have a grid somewhere. So that grid, you connect the incoming signal from the aerial to that particular grid. Why? This affects variation of the intensity of the beam as it sweeps across the screen. How? Dots of varying brightness in successive lines build up the image on the screen. So since this occurs at very high frequency, there is persistence of vision, which gives an impression of a steady picture. So when you connect the aerial, notice that the aerial will trap the signal as electromagnetic waves. I believe this we shall be able to cover, be covered in the upcoming topics, in which we shall look at suppose it's electromagnetic induction, not yeah, it should be under electromagnetic induction, yeah, spectrum, not electromagnetic spectrum, in which we are going to be able to look at various functionings of the spectrum, and also how it affects the specific waves. And basically this comes under waves. So basically, so it's like I confuse the topics, electromagnetic spectrum. When you are looking at the various waves, we have radio waves, we have microwaves, we have X-rays, we have all those kinds of waves. So basically, it is trapped as electromagnetic waves by the aerial, and the moment it goes through the wire to the television, it comes as electricity, but at different signals. So the moment it's connected to the grid now will be changing the frequency depending with the images that are represented by those signals, because those signals are basically sound and the picture that you should be able to see on the screen. So when you connect it to the grid, it now makes an impression of a steady picture, instead of now connecting it far away on different machines, so that it can come through a series of components before it reaches the grid. It's just connected directly to that particular grid, so that it creates an impression of a steady picture. Now, a color television has 3 electron guns. That's something you need to note. So there are 3 electron guns. Now, each carrying a color detail of one of the 3 primary colors, red, green, and blue. So the screen has a matrix of different color emitting phosphor dots, such that when they are stimulated, they give the color pictures. So that's basically the advancement on the television tube from a normal cathode ray oscilloscope or a cathode ray tube into what we have as a modern television tube. So with the time, you can just become an engineer, and be a careful one. If you want to study this one clearly, go open up the television, especially to start with the old ones. If you can access one, try studying them up on your own, so that you may be able to see clearly the components. And if you have a challenge, you can be able to get the connections through, so that you may be able to work on it one-on-one, so that it's more clear. And with the time, if you get the permission, you can even open up the modern one that you may have, so that you may see now the advancement and appreciate much more of what you have been able to get. So that's basically what was all for us in this topic, cathode rays tube and cathode rays. So success in your preparation, and may God bless you abundantly.